In today's lesson, we are going to look at rates, ratios, and percents. So this is the final lesson in our prerequisite skills kind of mini unit at the beginning. It's the last thing we're going to kind of look at in terms of prior knowledge. So we're going to look at how to kind of convert between fractions, ratios, percents, and rates, and really focus in on kind of unit rates and the such. So before we get into that, there is a kind of warm-up game that you can play. So if you have any linking cubes at home, you can feel free to kind of play this game. So the idea is it's kind of like a 3D Sudoku. So you're going to build towers in each square, and the towers are basically going to be sized from 1 block all the way through 4 blocks. So you have 1, 2, 3, and 4 blocks, or different towers of those sizes. So each row has skyscrapers of different heights, and there's no duplicate sizes. Each column has skyscrapers of different heights with no duplicate sizes. So similar to Sudoku, each column and row has different numbers, and there's no duplicates. The rules on the outside in gray tell you how many skyscrapers you can see from that direction. So if you put a taller skyscraper in front, you won't be able to see the ones behind it, and so on. So for example, here we can see an overhead shot of a 4x4 city block, and we have different colored towers. So you can notice how in each row, so going down, each row, they're different sizes. We have a 1, a 2, a 3, and a 4 block going in each column and each row. So that was the column I just mentioned. In the row, 1, 2, 3, 4 blocks. Right, and you can see in each other one, it's the same combination. So 1, 2, 3, and 4 blocks. Below is the front view. So here you can see how even though it was a 4x4 grid, we can only see so many towers in each row. Here we can see 1, 2, 3 towers. So the fourth one is hidden behind or in between somewhere. Here we can see 1, 2. The rest are hidden behind. Here we can only see 1, and here we can only see 2 towers. So those are what the numbers that are on the outside. So as an example, here's a grid. The numbers on the outside tell you how many towers you can see. And then on the inside, again, you need to have, say, the different numbers. So 1, 2, 3, and 4 block towers, different rows, or each row and each column can't have repeating sizes. So again, if you have the linking cubes at home, or maybe like Lego blocks or something like that, feel free to kind of play this or try out this activity. If you don't, we're going to be moving on then into rates, ratios, and percents. So just as a quick overview of all of them, we have a ratio, and a ratio is a comparison of quantities measured in the same units. Essentially, you're comparing one part to another part. So visually, we can see 2 to 3, or say 2 to 3, or use the colon. Either way, it still represents a ratio. So in our example, if we have a drink mixture of 4 parts juice and 3 parts soda, if I wanted to create a ratio of juice to soda, I would put the parts of juice, so in this case 4, as a ratio to the parts of soda, 3. If it was soda to juice, the parts of soda would come first, and the parts of juice would come second. In a fraction, what we're doing is we're comparing a part to the whole. So it's still in the same units, but we're comparing a part to the whole. So as an example, we've dealt with fractions in the previous lesson, but here we can see 2 over 5. That's a fraction. 2 parts, and in the whole, there's 5. So in total, there's 5 parts. So if I'm looking at soda, if I wanted to create a fraction for soda, it would be 3, because there's 3 parts of soda, over 7, because there's 7 total parts. You can put that up here in a different color just to remind us, 7 total parts. So that is the denominator. For juice, juice would be 4 parts of juice over 7 total parts. Moving on to a fraction, or sorry, a percent basically the term actually means out of 100, and it's basically a comparison to 100% or a whole. So we can see it sometimes represented as a decimal, 0.4, or as a percent, 40, or an actual percent, 40%. So to convert, if we start with our fraction 3/7 for soda, to get it to a percent, we first have to divide. So 3 divided by 7 gives us 0.429. And then to get to the percent, we multiply by 100. So this becomes 42.9%. Let me just keep this color coded. So to go from a fraction to a decimal to a percent, we have to divide our fraction and then multiply by 100%. In terms of juice, 4/7, again we're dividing. 4 divided by 7, we get 0.571. Multiply by 100, we get 57.1%. And you can round that if you really wanted to 57 and 43%. That still works as well. The last terminology we're going to look at, or last kind of overall definition, is a rate. And a rate compares quantities that are measured in different units. So we're going to be looking at things in different units. So for example, we may see things as kilometers per hour, right? That's comparing number of kilometers to a single hour. In this case, we may just see the word per, or we may see the slash, things like that. So this example of 100 kilometers per hour is actually what's called a unit rate. And it's called a unit rate because it's per one of something. So in this case, it's per 1 hour. So this is actually, again, like I said, a unit rate because it's per 1 hour. If it was, say, 200 kilometers per 3 hours, that's not really a unit rate. It could still be a rate, but it's not a unit rate. Unit rates are helpful because it gives us a better way to understand what's happening and a better way to visualize things or compare things. Right? If I say 300 kilometers in 4 hours compared to 100 kilometers per hour, it's a little bit harder to compare those two speeds. So, in our example, let's take the 300 kilometers in 4 hours and convert it to a unit rate. In other words, let's figure out how far we travel per hour. So when we're doing something like this, basically, we take our one number, 300 kilometers, divided by 4 hours, and all we do is we divide. So this gives us 75 kilometers per hour. Now you might be thinking, well, how do I know what number to put on top? Why don't I put the 4 on top? And that's a good question. When we use the units, because it's kilometers on top, it would be kilometers per hour. And you can see that in the visual, kilometers per hour, and it looks like a fraction of the units. So again, same thing over here in our example. If we were to divide kilometers by hours, we get kilometers per hour. If you were to do it the other way, as an example, say 4 hours divided by 300 kilometers, you would get 0.013, and then your units would be hours per kilometer. So that means it takes you 0.013 hours to travel a kilometer. So again, if you want to figure out what number needs to go on top, take a look at the units and figure out what rate do you want. Do you want hours per kilometer or kilometers per hour? Either way still technically makes sense, and it's still describing the situation. But again, the rates or the units may not be what we're looking for or what we're used to. So in an example, let's determine the unit rates for the following situations. So 140 steps in 25 seconds. I want to figure out how many steps can I get per second. So in order to do that, because it's steps per second, steps is going to go on top, seconds is going to go on the bottom. I have 140 steps in 25 seconds. And then I just divide. And I get 5.6 steps per second. If I did it the other way, it would be seconds per step. So it would tell me how the time it takes to basically step on one step. For number 2, 12 oranges for $6.99. So again, here it depends on what we want to look for. Do we want to figure out oranges per dollar or dollars per orange? Again, it depends on what you want to look at. Maybe you want to figure out the cost per orange. So in this case, we would want dollars on top and oranges on the bottom. So $6.99 divided by 12 gives us $0.5825. We can round that to 0.58 or 58 cents dollars per orange. So again, that's a little bit easier to understand, right? It might be easier to visualize or understand or compare what's the cost per orange rather than how many oranges can I buy for $1. Lastly, 108 points in 82 games. Here I want to figure out how many points per game can I get. So again, points per game, so points is going to go on top, number of games is on the bottom. So we get 108 divided by 82. And again, you're dividing. So we have 1.32 points per game. Right, so it's a little bit easier to understand there, so you can kind of get a sense of how well you do. If you did it the other way, it'd be how many games does it take you to get a single point? Right, so it's a little bit, might not make sense in the context. So you have to use some kind of common sense in a way to figure out what makes sense given this scenario. So an example, at Zehrs, 12 cans of pop are on sale for $4.99 and a 2-liter bottle was $2.49. What is the better deal? If one can has 350 milliliters and again 2 liters is 2,000 milliliters, which one was the better deal? So in order to figure out which one is the better deal, I need to figure out or get a unit rate so that I can compare the two. So then the question now becomes, do I want the dollars per milliliter or how many milliliters can I get per dollar? Again, either way, it will still help, it will still give you a number that you can compare between the two. You just have to understand what you're comparing. So in this case, I'm going to say, figure out the dollars per single milliliter, right? Usually the unit rate is dollars per something when we're dealing with cost and money. So I need to figure out how many milliliters I have. The 2-liter one is very straightforward. We have 2,000, we're using dollars first. So $2.49 divided by 2,000 milliliters gives me 0.00124 $5 per milliliter. So again, it might seem, well, that's ridiculously small. There's no way that could be correct. It does make sense because you have to think a milliliter of pop is a very small amount. If we look at the can, we have 350 milliliters in one can, but we have 12 of them. So I'm going to do 12 times 355 and get 4,260. Now I can find the unit rate, so 499 divided by 4,260 gives me a value of 0.00117 dollars per milliliter. So if we look at the two and compare, we can see that the 12 cans of pop, even though it costs more, is the better deal because we are getting, or the amount or the cost per milliliter is technically cheaper. Now again, that may not always be the reason for why you buy things, right? Maybe you don't need 12 cans of pop, you just want a 12-liter bottle, you're just by yourself, amount of space, things like that. But if you're going based off of cost on its own or best value, you'd get the 12 cans of pop. In a school, the ratio of boys to girls is 4 to 5. There are currently 300 girls enrolled in the school. Determine how many boys are in the school. So this is kind of using ratios, and we're going to use equivalent ratios to help us figure out. So they're similar to equivalent fractions. So we have 4 to 5 in terms of boys to girls. That's what the ratio is. If there's currently 300 girls, I need to figure out how many boys there are. Let me just, oops. And what we can do is consider equivalent ratios. So if I know there's 300 girls, if I look at my simplified ratio of 4 to 5, if I figure out, well, what do I do to get from 5 to 300? In this case, I would have to multiply by 60. I'm going to have to do the same thing for the boys. I'm going to multiply it by 60. So in this case, 4 times 60, 240 boys. So it's just basically an equivalent ratio similar to equivalent fractions. We need to figure out how would I go from 5 to 300 in terms of multiplying, and I do the same thing then to the number of boys to figure out how many boys are actually in the school. A basketball player scores 28 points in a game. She scores 35 of the total team points. How many points does her team score in total? So here, we need to figure out, we know she scores 28 points. And we know that this is equal to 35% of her total team points, or of the total team points. If I want to figure out how many points her team scores in total, I need to come up with fractions. 35%, we've talked about, is a percent, or basically per 100. So 35 over 100 is the same thing as 35%. Now, again, we're trying to create an equivalent fraction. Her 28 points out of an unknown total would have to equal or be equivalent to 35 over 100. So I can figure out, if I know how to go from 35 to 28, or figure out what that value is, I can then use that same value to go from 100 to the other one, or to my unknown. If we're not sure how to get there, what we can do is we can do 35 divided by 28 to figure out what is my multiplier there. What do I have to multiply 28 by, or sorry, 35 by to get to 28? No, the 28 to get to 35. How many times does 28 go into 35? It goes in 1.25 times. So that means if I want to go from 35 to 28, I would have to divide by 1.25. because it's an equivalent ratio, I have to do the same thing with 100. I have to divide 100 divided by 1.25, and that will tell me what my value is, or my unknown value is. In this case, it's 80. So that means the total team points is 80. If you want to double check your work, you can do 28 out of 80 total and see, does that work out to 35%, which it does. Another example, Austin Matthews scored 35 goals and had 28 assists last year. How many assists is he expected to have if he scores 500 goals this year? So again, it's the same idea of coming up with an equivalent ratio or an equivalent fraction. We know he has 34 goals to 29 assists. If he has 50 goals, how many assists is he expected to have? So again, we need to figure out, well, what do I increase by from, or how do I increase from 34 to 50? And then I'm going to do the same thing to go from 29 to my unknown. So again, you can do it different ways. You can do 50 divided by 34. Just figure out how many times does 34 go into 50. Which is 1.47. So if I do 34 times 1.47, I get my 50, or close enough. It might be a slight rounding error. So that means for the assists, I multiply them by 1.47 as well, and that gets me to my expected number of goals, which in this case 29 times 1.47 equals rounded 43. So therefore 43 assists are expected. And then lastly, a party tray of pizza with an area of 340 inches squared has 400 grams of cheese on it. How much cheese would a large pizza with an area of 190 inches squared have on it? So again, same idea. We're creating a ratio or a fraction. We're trying to come up with an equivalent one. So in this case, 340 inches squared to 400 grams of cheese. That's what we know. And we want to figure out, if I have 190 inches squared, how many grams of cheese will I have, or can I expect to have? So again, we need to figure out, well, what do I need to go by to go from 340 down to 190? Again, we can do 190 divided by 340, 0.56. So that means I would have to multiply 340 times 0.56. 340 times 0.96 or 56 to get to 190. I'm going to have to do the same thing on the other side. Multiply by 0.56. If I multiply 400 times 0.56, I end up with 224 grams. So again, the math was 190 divided by 340 equals the 0.56, which is what I multiply by. So again, therefore, it would have 224 grams of cheese. So again, the main thing in this lesson is being comfortable with determining the unit rates, as well as working with equivalent fractions or ratios. Right? It should be, again, review of some kind of prerequisite knowledge that you should have some grade 8 and some kind of mathematical reasonings. But again, if not, please make sure you are comfortable with these concepts and with the math that we're doing.